So as we said in class, electric fields are electric force fields, and so often we do calculations where we're transforming back and forth between force measurements and electric field measurements and electric field measurements to force measurements. So this is an example, a simple example of how you might do that in a problem. So you've probably noticed that if you pull a piece of Scotch tape off of another piece of tape or a smooth surface, it's left with some charge on it. And you can see that because the tape is attractive to other items, just like we kind of did in class with pieces of paper and pith balls and so on. So imagine I take a piece of tape and I charge it, and it produces a uniform electric field of strength 6,500 newtons per coulomb in the plus x direction. And what I want to know is, given that electric field, what is the force that these two charges might feel? Okay, so let's talk about that problem for a minute. So when you read problems, one of the things you have to do is you have to parse what kind of information you're given. And very often there are important elements of the problem that are stated kind of in passing, but are relevant to the way you solve the problem. And in particular, in this problem statement, you might look at it and say, wow, I'm not told everything I need to know. I'm not told how far away those two charges are from the piece of tape. And you're right, you weren't told, because it's not relevant to the way the problem was stated. The key thing in this problem, the kind of hidden bit of information, is this statement right here, which is that we have a uniform electric field. What that means is the field strength is constant no matter how far away you are from the piece of tape. And that's why you weren't told the distance. So parsing problems and figuring out what those little bits are is probably one of the hardest things that you have to learn to do when you're solving these problems in physics. Okay, so given that, this becomes a problem of just recognizing how force and electric field are connected by definition. So we said that the electric field was given by the force that would be felt by a test charge of a given size. Okay? Now this problem is a one-dimensional problem, but this statement is actually a vector statement. I should have vectors over the e's and the f's. Okay? Because we're doing it in one dimensions in the x direction only, you can, and you probably should, be cognizant of the fact that this is a vector problem, but we can use signs in the problems, pluses and minuses, to indicate the direction in the problem and not carry around all the klutzy vector notation. If we were doing this in a full two-dimensional vector problem, and we'll do some examples of that, then you absolutely need to remember the vector behavior and calculate the components of the vector. But in one dimension, we can drop, as we often have in the past, the vector notation and just use the sign to indicate, are we going to the left or are we going to the right? Okay, so we're interested in the force, and we're told the values of the test charges, and we're told the value of the electric field. So this can be rearranged to tell me that the force is simply the value of the test charge times the value of the electric field wherever I've laid that test charge down. Okay? So we're giving two charges. So in the first case, we're given the electric field is 6.5 times 10 to the 3 newtons per coulomb, and the charge we're given is 6.7 times 10 to the minus 6 coulombs. Okay? Now, if I multiply those together, I get plus 4.36 times 10 to the minus 2 newtons. Okay? Now, a positive charge is repulsed by positive charges. That's what we learned when we first studied Coulomb's law. When we took Coulomb's law and we turned it into a descriptor of electric fields, we said that electric fields point in the direction that positive charges feel a force. So in this case, we said the electric field in the problem statement is pointing in the plus x direction, so a positive charge should feel a force in the plus x direction, and indeed this is what this plus tells us. This is in the plus x direction. Okay, let's do this for the other charge. So for the second charge, we again have our 6,500 Newton per Coulomb electric field, but the charge in this case was minus 3.14 times 10 to the minus 6 coulombs. And if I multiply that out, I get minus 2.04 times 10 to the minus 2 newtons. If a positive charge is pushed, feels a force in the direction of an electric field, then the negative charge feels a force in the direction opposite to the electric field. The electric field points in the positive x direction, so our negative 3 microcoulomb charge should feel the force in the negative x direction, and indeed, that is what that minus sign tells us there. It tells us that this points in the minus x direction. Now, when you're solving problems, particularly on exams, you may solve a problem and leave it with a plus or a minus sign, okay? And in your head, it may be clear that that means the direction, but it may not be obvious to anyone reading your solution. And so it is proper practice to always write down the actual direction if you're not using vector notation, writing down the components. Okay, so that's that problem. We'll do another one soon. Good luck.